is an absolute value equation. And just to remind you, if I said absolute value of x equals 5, remember that we have x could be 5 or maybe x could be negative 5. Either one, because they're both 5 away from 0. So remember, absolute value is saying basically what is the size of the number and ignore the sign, or how far from 0 is the number. So both 5 and negative 5 are 5 away from 0. Because of that, that means we have to count for both cases. We called one the opposite or negative, and the other just the normal or positive case. First thing you want to do, though, is to get the absolute value by itself. So we have 2 steps in this one to do that. So we're going to subtract 4. Don't lose the negative on the absolute value. But also remember, absolute value is a function, so we can't just distribute the negative. It's not like parentheses. Okay, but now we can divide it off to get rid of it. We can just divide by negative 1, and that gets rid of the negative on the left side. So we'll have 2x plus 9 in the absolute value equals 21. Okay, from there, this is where we split and consider both versions. And so I'll call it probably just the normal and the negative or the opposite. And we take the opposite of the right side, just for convenience. So we drop the absolute value, and on this left side, it's just the normal version. On the right side, it's negative 21. Otherwise, everything else is the same. But that allows us to get rid of the absolute value. Okay, from here, it's pretty normal, just linear solving. So subtract 9, and we'll get 11, and then divide by 2. It's 12. That's what I said. Thanks. And we'll get 6. And then on the other side, same thing. We just end up with a different result. So we're looking at D, looks like. So 6 and negative 15. How'd you do on that one? It's honestly just normal solving with the exception of splitting. And then you just have to do it twice. Okay? Number 3, 4 functions are graphed. Which statement could be true? If you look at the theme of the equations or the statements, it's all just asking about which one is kind of the flipped version or the negative version of the given one. So we first look at D and C. So D and C, do those look like one's just the negative version? Like, what does putting a negative sign out front of a function do? Do you guys remember transformation stuff? It just reflects it over the x-axis, right? Just if you put it in maybe something more familiar, if I said f of x is x squared and g of x is negative x squared, remember the f is up, the g is down, it just reflects over. Well, C and D don't even look like the same function, so probably not that one. How about D and B? Yeah, like just flipped over, right? That looks pretty promising. I might mark that one and come back to it. C and A, well, those are reflections of each other, but which way? Yeah, so for that to be true, it would have to be C of x equals A of negative x. And the negative would have to be put inside parentheses. That's the y-axis reflection. Okay, and then A and B, those don't even look alike at all. So now we know it's B. So that was just checking, do you know what a negative sign out front does? Okay, number 4, find f of negative 8. So this is not solving for x. It's just taking negative 8 and plugging it in for x. And then giving your answer, okay? So if we write this out, we get absolute value of negative 8 plus 2, and then 4 minus negative 8 squared. So what's the numerator? Negative 8 plus 2 is negative 6. Absolute value of that is 6. Okay, what's negative 8 squared? 64. And then we have 4 minus 64. So negative 60. What is that in simplest terms? Negative 1/10. Okay. Hold up how many you got out of 3, please. dB and negative 1/10. Okay. Good review of some stuff we've done. Actually, all of that we've done in some version. And let's go ahead and check your homework. Raise your hand if you did it. Wow, look at that. Good job, guys. Sweet. Here are your answers. Now, just want to point out, here's what you're looking at in terms of checking your work. The second one, I wrote the answers a little different than I showed you because there are 2 ways to do it, and this is the other one. So the second parentheses is your quotient. That's what you should be checking that you've divided correctly. So 3x plus 1, 2x minus 3. Okay, next row. 7x minus 10, and then your remainder was 15. Okay, number 4, 4x plus 9, remainder 19. Number 5, negative x cubed plus 3x minus 2. Okay, remember we had this 0 where the x squared would go. So you don't need to write that 0x squared in your answer. You can, but you don't need to. Okay, number 6, x squared plus 4x plus 4. On the back, number 7. Lots of 1s in that result. So x cubed minus x squared plus x minus 1, and then remainder 2. Number 8. X cubed minus 3x squared plus 9x minus 27 plus 90 for the remainder. Number 9. X cubed minus 2x squared plus 4x minus 8, and then the remainder was 0. Number 10. Guys, it meant the same thing. It was just shown in a different form. But still, we're just dividing. And there, I'll let you just read that. Don't put that sheet away. Keep it out. We need it here in just a bit. Do you have it? Where? Yeah, put it. Don't put it away. Sophie, you need to keep better track of her. Okay. I want you, this back page is a good thing to notice this from. So look at yours if it was good. Look at mine if it wasn't. And first thing I want you to notice is every one of these, and all of them, we start with 1 degree higher than we end with. So 4 to 3. 4 to 3, 6 to 5, and 4 to 3. So synthetic division, or actually division in general, but especially synthetic, drops the degree. Synthetic division specifically drops it by 1 each time. So we wrote that in your notes. But if you ever get stuck on how to interpret this stuff, remember it's just dropped by 1 degree down. How'd that go for you? Give me a fist of 5 on synthetic. Overall, really, really good. You like it better than long division? Okay. Good. You do need to be able to do both, but you'll be doing synthetic a lot more often. So we have 2 theorems to talk about today. They're pretty easy, pretty interesting and easy. will you go shut the door, please? Thank you. So grab your notes and keep this sheet out. We're coming back to it. Like I said, keep it out. All right. Guys, there's a lot of talking and it's starting to be hard to talk over. So clean it up. Feel free to go outside if you need your conversation completed. You guys have a quiz on Thursday. An actual one. So I do have the one that you did last Friday or Thursday, whichever day we did. The check-in quiz. If you want yours, come up to me after class and I'll get it out for you. And you are free to keep that one to study from. But your quiz will cover what we've done so far. Let me remind you what that is so you can review. First one, or the first section was end behavior, sketching graphs based on descriptions, and the turning points, that kind of stuff. Second section was adding and subtracting and multiplying. And then third section was division. Both kinds, long and synthetic. And now today's work will be on there as well. So I think tomorrow we'll spend reviewing, and then Thursday we'll take that quiz. But not the whole period. We're going to move on probably about 2/3 of the way through the period. So you'll need to be efficient at your work as well. Okay, like I said, we have 2 theorems to talk about today. One I've already introduced to you, and let's start with it. So the factor theorem, it's got a super creative name. The factor theorem states that the expression x minus a is a factor of the polynomial if and only if that result is 0. In other words, if your remainder is 0. Or if you plug a in to the function and you get 0 as your answer. Either one. Okay? We've seen that before. I've kind of started asking you like, hey, is this a factor? And you've been able to tell me yes or no, just by looking at the remainder. Okay? The remainder theorem is kind of interesting. Here's what it says. I'll let you read the wordy version, and then I'll tell you like the more normal human version. So the remainder theorem states if a polynomial p is divided by x minus a, the remainder is p of a. What does that actually say? Can anybody put that into like a simpler version? What does p of a mean? Okay. Good try. I think let's just write it in your notes in the simpler version, since that version doesn't really help. Guys, this theorem is... Actually, I'll just tell you as I write it. This theorem is a convenience theorem, in my opinion, meaning it can help you shorten your work for certain applications, but it's not a critical theorem to know or to use. Like I said, though, it can make life easier sometimes. Here's what it says. In plain English, it says this: the remainder of synthetic division by x minus a is the same as what you get if you plug A into the function. So how is that a matter of convenience? Let's maybe make this just a bit more clear. So I'm going to take 2 boxes for this. Okay. So set up, like let's pretend we have some number, right? We have all this synthetic division. And we get this remainder here. That is the same as if I plug A in to the function and get the result. Meaning, like, make all the x's A, okay? It's the same. Now, sometimes synthetic division is way faster than plugging it into a function. I'll show you what I mean in a second. Especially after all the practice you guys did on this, I think you would agree. So I'm going to put the example for this right here because I don't want you to have to flip back and forth. It's a short example. Let's say our function was this. So 2x to the 6th plus 4x to the 5th minus 3x cubed plus 7x squared minus 3. And I want to know what f of 5 is. Now, how much of a pain would that be to stick 5 into that function and evaluate it? Like, do you know what 5 to the 6th is right now? No. How about 5 to the 5th? 5 to the 3rd is 125. So you get an idea of the size of numbers we're dealing with here, right? So that would be a real pain, okay? I'm going to say plugging in 5 for x is horrible. Especially without a calculator. But what this theorem says is that we don't have to. We can just do synthetic division instead. And that's the same. Go ahead and set that up. What is A? Well, A is 5, okay? And then we run across here 2, 4. We skipped to the 4th. Negative 3, 7. We skipped x and then negative 3. What's the first step? Bring 2 down. Good. And then multiply. So 5 times 2 is 10. And we get 14. 5 times 14 is 70. Add, we get 70. 5 times 70, 350. Subtract 3, essentially subtract 3. 347. Okay, this is not as fun.
Negative 347?
What? Yeah, why did I put a negative there? Thank you. Let's see, that's 1500 plus 20, so 1700 plus 35. So 1735 plus 7 is 1742. Okay, and now we're doing 5 times that. So 5,000, 3,500. What did I say? 5,000, 3,500 is 8,500. Thank you. Did you say that? 8750? 8710. 10. Thank goodness for those zeros, right? Okay. And then 40,000. 43.5. And then 43,550. Now I picked a hard example, but we got there. Okay. Anyway, off to the side, write this. This is f of, this is not if, this is f of 5. Okay? That's all that one says. Now, I don't know if that was better for you. It was definitely better for me. I would rather do that than plug it into x to the 6th, 5th, 4th, all that stuff. Because at least I could do it in my head this way. Okay? But do you see how it's still just a matter of convenience? All right. That's the remainder theorem. Here's the factor theorem. This one is not a matter of convenience. This one is crucial. Now, fortunately, this one is way easier. But please, please know this one. Here's what it says. If the remainder, we're going to write the most basic version of this, is 0, the divisor. You guys clear on what I mean by a divisor? I'll put it in here so we just don't have to worry about it. What do I want to say? The expression. That we divided by. So make sure you emphasize the word by. It's not what's being divided, but what's divided by. Anyway. If the remainder is 0, the divisor is a factor. That is something you've already been telling me. Last week when we got a 0 on our remainder and I said, is it a factor? And you would say, yep, that's the factor theorem. Okay? Now, why does that matter? Well, we want to factor. That's the whole reason we're dividing, by the way, is to find factors. So we can break it down from 5th to 4th to 3rd to 2nd and then use the quadratic formula or maybe the star. Okay? This one's huge. Know it. So look at your sheet now. Pull that one from homework. Don't shout this out, but I want you to tell me which ones of these the divisor was a factor on. Maybe go circle the problem number for the ones that the divisor was a factor. Did you not do it? You did it. Go circle the ones that it was a factor. Okay, that shouldn't have taken very long. But here's what we're seeing. Number 1, 3x plus 1, x plus 2, the thing that we divided by, that's a factor. That means we have a 0. So what would be the 0 of that factor? -2, right? Okay, so we know, like if I said go graph that, you know you have a 0 at -2. Okay, number 2, x plus 5 is a factor. Go write this so you have this to reference later on. What is the 0 for that one? -5. Okay, how about 3 and 4? Was the thing we divided by a factor? Nope. So, not a factor. All right, number 5, factor. What was the 0? Yep. Okay, x minus 1 in number 6, x minus 1 was a factor. And what was the 0? +1. Okay, how about 7? Not a factor. 8. Not a factor. 9. 9 was a factor. This one came up a lot on this sheet. 0 was. Okay, how about 10? Not a factor. Okay. So this is the goal of division mostly for us, is identifying factors. Let me explain the process that we're going to use. If I handed you this, not the x plus 2, but just the x cubed, or x to the 4th minus 16, and I said, please factor this. Okay, first of all, we'll have another theorem that tells you what to use to try. But let's say you pick -2 and you try dividing, and you get, hey, that's a factor. Sweet. Well, now you can take the cubic one and start dividing it. Instead of going back to the 4th, we've broken it down a layer. So we could now pick a different number and try dividing this new polynomial, the broken down one. And if we find one that works, now it's going to be a quadratic. And by the time we get to quadratic, we don't have to divide anymore. We can just either star or use the quadratic formula to find our other zeros. Okay, so we can take this like 6, 5, 4 just by division as long as we're finding factors. Go back and look at number 6, please. This is a real good example. If I said factor this, and you tried +1 as a potential factor, well, you go through your synthetic division. It takes you like 20 seconds. And you figure out, hey, I got a 0, so that's a factor. I have successfully broken it down to a quadratic. Everybody factor this now, please. Just take maybe 30 to 45 seconds and factor that. And write this one in factored form when you're done. Okay, here's what you should have. So in your star, x plus 2 makes the x squared plus 4x plus 4. We already divided to find out that x minus 1 was a factor. So factored form is this here. And it wasn't given with an f of x, but it will be when we do this. So that is now factored form for that function. Where are our zeros? What's the 0 of this one? 1, -2, and that's the same, okay? So what we'll see, and this kind of completes the process, is if we see 2 of those like that, we use what's called multiplicity of our zeros to determine how the graph looks. And because that one, I'll just sketch it here real quick. We have a 0 at +1. Because that has 2, that tells us it bounces off. So it does something like this. Bounces there and then comes back through. And that's our graph. Okay? And of course we can find the y-intercept. If we go up here to the original, what's the y-intercept in here? -4, right? And so our graph is pretty darn good. If we took this to Desmos, it would look pretty much just like that. Okay, how do you feel about the 2 theorems, especially factor theorem? Are you okay with it? Okay, basically you're looking for a 0 remainder. As long as you have one, the thing you divided by is a factor, and you're happy because you have broken down your function. So tonight's practice